In this video, we're going to look at rational functions. There is a second video that includes some graphing, but in this video, we're just going to discuss how to find the important features of a graph of a rational function. So like I said, there is a second video that you can check out that actually takes you through the graphing process. So a rational function is of the form f of x equals g of x over h of x, where g of x and h of x are polynomials. The domain consists of all real numbers except for the zeros of the denominator. And first, what we're going to look at is how to find the intercepts of a rational function. So to find the x-intercepts, they are the real zeros of the numerator, assuming the numerator and denominator have no common factors. So let's take a look at this function. Whoa, f of x, not sure what happened there. Here, let me delete that. Okay, that looks better. Okay, so here's our function f of x. And let's factor it first, because to find the x-intercept, we need to make sure that the numerator and denominator have no common factors. So that numerator factors as x minus 4 times the quantity x minus 3. To factor that, I just looked for two numbers that add to -7 and multiply to 12. I'm going to do the same thing for the denominator, looking for two numbers that add to -2 and multiply to -8. That would be -4 and +2. Now that I've factored both the numerator and denominator, I can see that they do have a common factor of x minus 4. So I'm going to get rid of that common factor there. And my reduced function is x minus 3 over x plus 2. So the x-intercepts, actually there's only going to be one. There's one x-intercept. And to find that one x-intercept, I'm going to find the 0 of the numerator, meaning that I'm going to solve this equation here. And when I solve that equation, I get x equals 3. So I have one x-intercept, and that is the point 3, 0, if you want to write that as an ordered pair. So an x-intercept at 3, 0. I found the 0 of the numerator once I made sure that the numerator and denominator had no common factors. Now I just want to point out that we've discussed that to find the x-intercepts, we want to let f of x equal 0. And I just completely ignored the denominator. This is because if this rational function, or this, I wouldn't call it a rational function here, if that's going to be 0, it's going to happen when the numerator equals 0. That's how we're going to make this rational expression be 0. Now to find the y-intercept, we just have to find f of 0. And we can use the original function, or we could use the reduced function. Either way, we're going to get the correct answer. I'm going to go ahead and use the reduced function. And then so I'm going to plug in 0 for both x's, and I get -3 over 2. So therefore, my y-intercept as an ordered pair would be the point 0, 3 over 2. Now, we'll practice this concept again later, but first I just wanted to discuss how to find the intercepts of a rational function. So that's how we find the intercepts. The x-intercepts are the zeros of the numerator once we reduce the function, and the y-intercept is f of 0. We can plug in 0 for x into the reduced function or the original. Either way, we'll get the correct answer. Notice that if I had plugged it into the original function, plug in 0 that is, I would have gotten 12 over -8. But 12 over -8 is the same thing as, oops, I forgot my negative, I just noticed that, -3 over 2. Sorry about that, forgot my negative. Okay, now we're going to discuss asymptotes. This is a fun one here. Lots of information here. I'll kind of explain as we go, as we see the examples. We have vertical asymptotes, where we have, we look at the zeros at the denominator. That's going to give us our vertical asymptotes if they exist. We do have to make sure the numerator and denominator have no common factors. Once again, we've got a theorem on horizontal asymptotes. We have to look at the degree of the numerator and denominator in order to determine which of these three cases it's going to be. And then if we do not have a horizontal asymptote, there is the potential of an oblique asymptote. This is when the degree of the numerator is 1 bigger than the denominator. And we can use long division or synthetic division to determine the oblique asymptote. Synthetic division is probably the preferred way as long as our denominator is in the form x minus c. Okay, I know I just went through that really, really fast, but I'll explain as we go. Okay, so we want to find all asymptotes of this function here. First of all, we'll check to see if the numerator and denominator have any common factors, and they do not. I can factor the denominator. The denominator is a difference of squares, but it factors as x plus 3 times the quantity x minus 3. And there's x plus 7 is what our numerator is. So no common factors. So our vertical asymptotes are going to be, first we'll want to find the zeros of the denominator, which means that we'll want to solve this equation here. And when we solve this equation, we get that x equals -3 or 3. Those are our two vertical asymptotes. So VA for vertical asymptotes, we have two vertical asymptotes. One is the equation x equals -3, and the other is the equation x equals 3. So two vertical asymptotes. It is important that you include the x. Don't just say -3 and 3. These are equations of vertical lines, and vertical lines are of the form x equals some number. So we do need the x in there. Now, to determine the horizontal asymptote, if it exists, so horizontal asymptote, we have to look back up here at our theorem on horizontal asymptotes. What really matters is the degree of the numerator and denominator. Now, the degree is the greatest exponent. And so, looking at our original function here, the degree of the numerator is 1 because x to the first, so our greatest exponent of the numerator is a 1. The degree of the denominator is 2 because the greatest exponent in the denominator is a 2. We have an x squared. So we're looking at when the degree, so this is the case we're looking at right here, because the degree of the numerator is smaller than the degree of the denominator. That means that the x-axis, or in other words, y equals 0, is going to be the horizontal asymptote for our graph. So horizontal asymptote is y equals 0. Oblique asymptote is none. We're not going to have one. We're only going to have an oblique asymptote when the degree of the numerator is 1 bigger than the degree of the denominator, so 1 greater than. So no oblique asymptote for this one. Okay, we're going to see 2 more of these because these are kind of tough, figuring out the asymptotes. Okay, so here's our next one. First thing I'm going to do is I'm going to factor and see if our numerator and denominator have any common factors. It looks like it's going to be a no again. They don't have any common factors. So I just wanted to make sure I do that first because that's going to affect our vertical asymptotes if we have a common factor. So I looked for 2 numbers that add to 7 and multiply to -8. Those 2 numbers were +8 and -1. So no common factors. So our vertical asymptotes, there's just going to be one of them, and we need to find the zeros of the denominator, or the zero, singular in this case. So one vertical asymptote, and that is x equals -2. Horizontal asymptote is going to be none. And I'll explain why. It all has to do with degree. So the degree of our numerator this time is 2, because the greatest exponent is 2. The degree of our denominator is 1, because the greatest exponent is 1. We have an x to the first. If we go back and we look at our theorem on horizontal asymptotes, if the degree of the numerator is larger, so let me erase this because we don't have that anymore. That was example number 2. This time, the degree of the numerator is larger than the degree of the denominator, and that means that there is no horizontal asymptote. All right, so no horizontal asymptote for this one. We do, however, have an oblique asymptote for this example. So let's talk about how to find the oblique asymptote. The oblique asymptote occurs when the degree of the numerator is 1 greater. Okay, we do have a degree of 2, a degree of 1. The degree of the numerator is 1 bigger. And the way we find this is, well, we can use synthetic division here. You could also use long division, but I'm probably going to recommend synthetic division. I think it's going to be a little bit quicker. And when we use synthetic division, we first put C in the box. C is -2. This is because we consider our divisor of the form x minus c. There is a separate video that covers synthetic division. So if you need some extra help with synthetic division, check out that video. I'm going to go through this pretty quickly because, hopefully you've watched that video, or you feel pretty comfortable with synthetic division. So I'm using synthetic division here, and this last number here is my remainder. This is my constant or number term, and this is my coefficient of x. The remainder is not used in the equation of the oblique asymptote, so we're not even going to use the remainder. An oblique asymptote, I'm going to scroll back up here for just a second. It's of the form y equals ax plus b, and our a and our b come from our division, our long division, or in this case, synthetic division. So this is going to end up being your a right here. So this will be our ax. This will be our b. So the equation of our oblique asymptote is going to be y equals ax plus b. So it's going to be 1x plus 5. So we do have an oblique asymptote, y equals x plus 5. We're going to graph in the next video, but just to kind of explain this, this would just be a line with a y-intercept of 5 and a slope of 1. All right, one more like this, and then we're going to put it all together here. We're going to find intercepts, we're going to find asymptotes, and then we're also going to talk about something called a hole. That's actually going to occur here in this next example. Okay, so before we find the zeros of the denominator, in order to determine our vertical asymptotes, I first need to make sure that the numerator and denominator have no common factors. So in the numerator, I do notice I have a GCF of x. And so I'm going to first factor out that GCF. In the denominator, I can factor that trinomial. It'll factor into x minus 3 times the quantity x plus 1. And I looked for two numbers that add to -2 and multiply to -3. I can take the numerator a step further. I do have a trinomial inside the parentheses that factors. So I am going to continue and factor there. And then I notice that I have a common factor in the numerator and the denominator. So I'm going to go ahead and get rid of that common factor. And now I have this reduced function. So because I was able to cancel a factor of x minus 3, I only have one vertical asymptote. That one vertical asymptote is the equation x equals -1. So I do not have a vertical asymptote of x equals 3. When we determine vertical asymptotes, we look at the reduced function and find the zeros of the denominator. Okay, so vertical asymptote, we've got 1, it's x equals -1. Horizontal asymptote, I do not have one again because the degree of the numerator is larger. The degree of the numerator is 3, and the degree of the denominator is 2. And so if I look back here, I'm going to scroll back to my previous page. It's still starred. We've got a numerator that has a larger degree than the denominator, so there would be no horizontal asymptote. We do, however, have an oblique asymptote again because the degree of the numerator is 1 larger or 1 greater than the degree of the denominator. And to find this oblique asymptote, we could use long division, if you prefer that, or synthetic. I think I'm going to use synthetic because I just feel like that goes a little bit quicker. I'm going to use, in order to use synthetic division, we do need to refer to the reduced function because I cannot use synthetic division with the original function because my denominator is not of the form x minus c. So I'm going to look to this reduced function here. So I'm going to put my c in the box, and I'm going to write my coefficients of the numerator up here. I do not have a constant, so I'm going to go ahead and put in a 0 there. And I'm going to perform synthetic division. Again, I'm going to do this pretty quickly, but there is another video on our YouTube channel that you can watch. This is our remainder. This is our number term or coefficient of x. I'm sorry, number term or constant, and this is our coefficient of x. We don't use the remainder at all. So the oblique asymptote has the equation y equals x minus 7. Okay, so I'm getting that from looking at the result or my quotient when I divide the numerator by the denominator of the reduced function. So y equals x minus 7. You would get exactly the same thing if you used long division and you use the original function. We would still get y equals x minus 7. Okay, so these are 3 answers. We end up having 2 asymptotes. Okay, now there's something else, like I said, that we need to talk about, which is a hole. So down here, this paragraph here is pretty important. So it says, although there is no vertical asymptote x equals 3 in the example 4 above, something does happen when x equals 3. There is a hole in the graph. That is a single point missing. And if we want to find the y value of the hole, we can substitute 3 for x in the reduced function. So there is a hole in the above function, or in the graph of the above function. And to find the hole, since we had a common factor of x minus 3, that means the hole is going to occur at x equals 3. So we get the x coordinate by setting that factor that we canceled equal to 0. So the hole occurs at x equals 3. And to find, so the x coordinate of the hole is 3. To find the y coordinate, we are going to find f of 3. But we need to not plug it into the original, but plug it into the reduced. If you plug it into the original function, you're going to get 0 over 0, which is undefined. So that doesn't help. we want to plug it into the reduced function. So we'll have 3 squared minus 6 times 3 over 3 plus 1. This would give us 9 minus 18 over 4, which is negative 9 over 4. So our whole occurs, the coordinate or ordered pair of the whole would be 3, negative 9 over 4. So we do have a whole for the above function. As I mentioned a couple times already, there is another video of graphing. And so we'll discuss in that video how to graph a whole. It's really just like a single point missing. It's just going to be an open circle just in the middle of your curve. Okay, one last example for this video. We're going to put this all together. So at the very beginning of the video, we talked about how to find intercepts. Then we talked about how to find asymptotes, and then we just saw a whole. So perhaps this function will also have a whole. So we're going to put it all together. We're going to find these 6 items here, if they exist. Okay, so putting it all together. First thing I should do is I should factor and cancel any common factors in the numerator and denominator. So in the numerator, I can factor out a GCF of 5x. Be left with x plus 4. In the denominator, I can factor that trinomial. It factors as x minus 7 times the quantity x plus 4. I looked for 2 numbers that add to negative 3 and multiply to negative 28. I do notice that I've got a common factor in the numerator and the denominator. That common factor is x plus 4. And so my reduced f of x is going to be 5x over x minus 7. Now, because I had this common factor, I am going to have a hole in the graph. And that hole is going to occur at negative 4, an x coordinate of negative 4. This is because if you set that factor that you just canceled equal to 0, we get x equals negative 4. Now, I can find the y coordinate. In fact, why don't I do that really quickly? I don't have to find these in any particular order. Let me go ahead and finish the whole. So to find the y coordinate of that whole, I'm going to find f of negative 4. I do need to use the reduced function, not the original function. If I use the original function, I'm going to get 0 over 0, which is undefined. So that would not be helpful. So I'm getting negative 20 over negative 11. A negative divided by a negative is a positive. And so the y-coordinate of the whole would be 20 over 11. Okay, so we found the wholes. That is done. To find the x-intercepts, we want to find the zeros of the numerator. Now we have to make sure that we cancel any common factors, so we're going to again use the reduced function in order to determine the x-intercepts. So I'm going to find the zeros of the numerator. There would only be one, and that would be 0. So we have one x-intercept, and that is the point 0, 0. To find the y-intercept, we're going to find f of 0. And to find f of 0, we can use either the original function or the reduced one. Maybe I'll just use the reduced one. I feel like it's, you have to, I can use, I'll get to work with smaller numbers there, I guess. So f of 0 is 0 over negative 7, which is 0. So I also have a y-intercept of 0, 0, and that makes sense. The two axes cross at the point 0, 0, so if 0, 0 is an x-intercept, it's also going to be a y-intercept. Okay, so I found this, I found this. Okay, vertical asymptotes. Vertical asymptotes, I look at the zeros of the denominator of the reduced function. And so I do have one x-intercept. It occurs, or it is the equation, I should say, x equals 7. Okay, I found that. Horizontal asymptote, if any. So this one is something, we haven't seen this scenario yet for the horizontal asymptote. The degree of the numerator is 2. So degree of the numerator is 2. The degree of the denominator is also 2. When the degree of the numerator and denominator is the same, or when the degrees are the same, then, so we haven't seen this yet. Let's go back up here. Let's scroll back up. This is the second bullet point here. So like I said, I haven't seen it yet. So now we don't have this condition anymore. There we go. We have this second condition here. So if the degrees of the numerator and denominator are the same, then the line y equals the ratio of leading coefficients will be the horizontal asymptote. Okay, let's see what the heck that means. So back to our example. So we have the same degree. When we have the same degree, we're going to take the ratio of the leading coefficient. The leading coefficient of the numerator is 5, and the leading coefficient of the denominator is a 1. Let's see a 1 there. So our horizontal asymptote is y equals 5 over 1, or y equals 5, because 5 over 1 is just 5. So y equals 5 is our horizontal asymptote. We took the ratio of the leading coefficients. All right, on the horizontal. And the oblique, there is none. The oblique asymptote, we're only going to have an oblique asymptote if the degree of the numerator is 1 greater than the degree of the denominator. So no oblique asymptote exists for this problem. Sorry, one more quick thing about the horizontal asymptote. I just want to mention you could use the original function to come up with the the horizontal asymptote. Notice that we could also use the reduced because our ratio of leading coefficients would still be 5 over 1. So you can use the reduced or you could use the original. We really could use the reduced for all of these. Some of them you must use the reduced function, but sometimes it doesn't matter. But I would say you could always use the reduced function to come up with these. The only time we wouldn't want to use the reduced function is if you were asked to find the domain, because the domain, we'd use the original function. The domain, we would say all real numbers except for the zeros of the denominator of the original function. But anyway, the reduced function can be used to find all of these, and sometimes it's necessary to use the reduced function. So I would just recommend using the reduced function. All right, well, thank you for watching this video. There's another video where we're going to use this information to plot a graph. So check out that video. That covers how to transfer this information to the coordinate plane.